Let's investigate the 3-qubit inverse quantum Fourier transform. In the previous videos, we saw examples of the quantum order-finding subroutine of Shor's factoring algorithm for the input n equals 15. We saw an example where a equals 11. That was associated with an order of 2. We also saw an example where a equals 7. And that was associated with an order of 4. In these examples, to go from the state in step 3 to the state in step 4, we applied the inverse quantum Fourier transform to register 1. And register 1 in these examples consists of 3 qubits. So that's why we have the 3-qubit inverse quantum Fourier transform shown over here in its matrix representation. We're going to investigate this matrix representation, and we're going to see how input states get mapped to output states. So this is the reasoning behind the steps in the previous videos, where we go from step 3 to step 4. And this is what's happening in register 1. So we're only applying the inverse quantum Fourier transform to register 1. And after that, we can measure register 1. So let's examine this notation over here. This f is for Fourier transform, and this subscript 2 to the power of 3, this is telling us the dimension of the Hilbert space. So we have 3 qubits. That means the dimension of the Hilbert space is 2 to the 3. That is 8. That is why we have an 8 by 8 matrix over here. And over here we have a dagger, and this dagger tells us that we are taking the Hermitian adjoint. So this is not the definition of the Fourier transform, this is the inverse Fourier transform. And that is a convention. It is a sign convention. So in previous videos, I defined the quantum Fourier transform with the opposite sign convention to this. So that means that this is the inverse quantum Fourier transform. You can use either convention, but it's important to be consistent with the convention choice. So that is what this notation is telling us. Over here we have a normalization coefficient of 2 to the minus 3 on 2. So this is just a normalization coefficient out the front. And we can distribute this into all of the entries in this matrix. Now let's have a look at what's going on in this matrix. There's a lot of interesting patterns. So in the black color over here, I've got the entry 1 and omega to the power of 4. In the blue color, we have omega to the power of 5 and omega to the power of 1, which is just written as omega. In the red color, we have omega to the power of 6 and omega to the power of 2. And in the purple color, we have omega to the power of 7 and omega to the power of 3. The terms which have the same color are actually additive inverses over here. So let's define what omega is. Consider the unit circle in the complex plane. Omega is going to be a slice of that unit circle. And because we're dealing with an 8-dimensional Hilbert space over here, we're going to slice up the unit circle into 8 slices. So you can think of this as a pizza, and we're slicing it up into 8 slices. So this is omega over here, and we can write it as omega to the power of 1. And you can see on the other side of the unit circle, we can find its additive inverse, and that is omega to the power of 5. So they have the same color, and they're showing up in this matrix in various locations. And omega to the power of 2 is the additive inverse of omega to the power of 6. So this over here is actually I, and this is minus I. So these are both additive inverses, and they're actually multiplicative inverses as well. That's because I times minus I gives you 1. So omega to the 0, that is equal to 1. Every time we see 1 appearing in this matrix, that is just omega to the power of 0. And when we just see omega by itself, that is omega to the power of 1. And we can also see omega to the power of 3 is on the opposite side to omega to the power of 7. So they are additive inverses. And omega to the power of 4, that is equal to minus 1. So here we have minus 1 on the left and plus 1 on the right. So they will cancel each other out. So it's the terms that are on opposite sides of the unit circle, they are going to cancel each other out. So when you add these in the complex plane, it's just like adding two-dimensional vectors. And if they have the same magnitude but the opposite direction, they're going to cancel and they're going to give the 0 vector. So this over here is the 0 vector if we're talking about a 2D plane and adding arrows in a 2D plane. But you can also think of it as 0 at the center of the complex plane. So that's the intersection of the real axis and the imaginary axis. So we've talked about these additive inverses. So these are inverses when we are defining the operation of addition. But we can also define multiplicative inverses. So let's have a look at these relationships over here. So here we have all of the powers of omega. So going from 0 all the way up to 7. And omega to the power of 8, that gets us back to where we started. So we have 8 slices, and that's going to take us all the way around the unit circle. So that's why omega to the 0 is equal to omega to the 8. It's also equal to omega to the minus 8. What does a negative exponent mean in this diagram? It means we're going in the opposite direction. So by convention, we are setting omega to be this value over here. We could also have chosen a different convention. We could have put omega down here, and then we would have been going around the unit circle in the opposite direction. And we can denote that with a minus sign in the exponent. So have a look at this pattern over here. Here we're starting from minus 1, minus 2, minus 3, minus 4, all the way up to minus 7. And minus 8 is the same as plus 8. That's because we're here at the identity. So this is the multiplicative identity, which is plus 1. So we're going all the way around the circle and coming back to where we started. So that's this value up here. And you can see that omega to the power of 1, well, its multiplicative inverse can be found by reflecting over the real axis. So multiplicative inverses are the mirror images of these states. So the multiplicative inverse of omega to the 2 is omega to the 6, which is also its additive inverse. That's very special. And omega to the 3, its multiplicative inverse is omega to the 5. So if we multiply omega to the 5 and omega to the 3, we're going to get the identity, which is 1. But if we add omega to the 3 and omega to the 7, we're going to get the additive identity, which is 0. So it's important to define which operation we're dealing with. Here we're dealing with addition, and over here we're dealing with multiplication. So graphically or visually in this diagram, you can think of as this winding around one direction or winding around the opposite direction. And that's what this minus sign is telling us. And this is also a sign convention. This is the difference between the quantum Fourier transform and the inverse quantum Fourier transform. In previous videos, when we looked at matrix representations for the 3-qubit quantum Fourier transform, we had a very similar diagram to this. But this column over here was swapped over with this column. And this column over here was swapped over with this column, and this column was swapped over with this column. But otherwise, we had the same patterns. Now, this act of swapping these columns around is the same as putting a minus sign up here. And that's the same as changing the convention. We're either going clockwise or counterclockwise around the unit circle in the complex plane. Now, let's have a look at the values over here. I've expressed all of the values of the powers of omega in the Cartesian form. So this Cartesian form is very useful. So now we can actually see what these values are in terms of 1 and I. So here we have plus 1, over here we have plus I, minus 1, and minus I. And then these diagonal values are sums of 1 and I. And you can see this normalization coefficient of square root 2. So we're dividing by root 2. That's because if we just add 1 and I together, we're not going to get a normalized vector. It's not going to be on the unit circle. So we have to divide by root 2, and that gets us back onto the unit circle. So we've seen the terms that appear in this matrix. And we've seen that they form pairs, which are additive inverses. So these are the additive inverse pairs. And then we also have multiplicative inverses. And these are also very useful. We're going to be using these pairs to evaluate what happens to the input states and which states they actually get mapped to. So let's have a look at this state over here. So this is a simple example where we initialize in the 0, 0, 0 state. So all of the entries in these column vectors can be numbered as 0, 1, 2, 3, 4, 5, 6, 7. So this is the decimal representation of these values. But we can also represent them in binary. So here we have strings of 3 bits. Here we have 0, 0, 0, and that corresponds to this 1 over here. So when we have a 1, that tells us that we have the presence of this state. And if we have something other than 1, then we have a phase factor. And if we have 0, that means the state is not present in the superposition. So this is what we would initialize the first register in. So in step 1 of the quantum order finding algorithm, we initialize the first register in the state 0, 0, 0. So all 3 qubits in this 3-qubit register are initialized in the computational basis labeled by 0. And we can write that condensedly as 0 in decimal. And we can also represent that as a column vector where we have a 1 over here and then 7 zeros. So where is this going to get mapped to? So if we take this matrix and we apply that matrix to this column vector, it's going to get mapped to this matrix. You can see a normalization coefficient has emerged. That's the same normalization coefficient that we have over here. And then we have produced a uniform superposition of all of the computational basis states. So there were 8 computational basis states in total. That is because we're dealing with an 8-dimensional Hilbert space. We have a 3-qubit system. That's this 2 to the power of 3. So this is what happens over here. And you can also achieve this by applying Hadamard gates to all 3 qubits. So first you initialize all 3 qubits in the first register in the state 0, and then you apply Hadamard gates to all 3 of them. And that's going to have exactly the same effect as this quantum Fourier transform. It's actually going to have the same effect as the inverse quantum Fourier transform and the quantum Fourier transform. That's because this 1 over here is only going to be affected by this column. So we're going to have 1 and then zeros, zeros, zeros. So all of these terms are irrelevant for this vector. And this column over here, column of 1s, that is shared between the inverse quantum Fourier transform and the quantum Fourier transform. And also, if we take the tensor product of the Hadamard with itself 3 times, we're also going to have this column appearing. So that is why we have this mapping. So this is a very important mapping because it allows us to see the conventions. We see which state corresponds to which entry in these column vectors. Now, when we're applying this big matrix over here, we're going to have more complicated examples. So let's move over here and see some of those more complicated examples. Let's see a superposition of all of the even values. So this is a superposition of all the even values, and this is a superposition of all the odd values. This is 0 over here, this is 2, and then this is 4, and then this is 6. Over here we have 1, then we have 3, then we have 5, and then 7. So these are all the odds, and these are all the evens. You can see that this string of 1s and 0s can be mapped back to a superposition of these computational basis states. So what happens if we only consider the even values in the input superposition? Well, first we have to have a normalization coefficient of 2 to the minus 1. Then when we act with this matrix onto this column vector, what is going to happen? Well, first let's consider the normalization coefficient. So we're going to have this factor from the matrix, and we're also going to have this factor of 2 to the minus 1 in the input. So this is the factor that is coming from the matrix, that's 2 to the minus 3 on 2, and then 2 to the minus 1 is coming from the input, and then we also have a factor of 2 to the 2, which is going to happen when we evaluate the sum of 4 terms. So we're going to have 1 plus 1 plus 1 plus 1. So that's 4, and 4 is the same as 2 to the 2. And if we multiply all of these factors together, we're going to get a normalization coefficient of 2 to the minus 1/2. And that is the normalization coefficient we have in the output. Now, let's see what's actually happening when we consider the even values. So this pattern over here, we're going to consider the even values along the rows. So in the first row over here, we have 1, 1, 1, and 1. So that's going to sum to 4, and then we can factor that 4 out. That's this 2 to the power of 2. So here we're going to get a 1. then the next 3 entries are 0. Why is that the case? Well, if we look at the even values, here we have 1, omega to the 6, then we have omega to the 4, and then omega to the 2. We have omega to the 6 and omega 2, they're going to cancel each other out, and omega to the 4 and 1, they're going to cancel each other out. So we can use this relationship over here. And we also have this relationship over here. So these are additive inverses, and they're going to cancel, they're going to give us the additive identity, which is 0. Now this also happens over here. We have 1 omega to the 4, 1 omega to the 4. So those cancel, and then here we have 1 omega to the 2, omega to the 4, and omega to the 6. So this 1 and this omega to the 4 cancel, omega to the 2 and omega to the 6 cancel. But then when we get to this term over here, that's the label where we have 4, we're going to have 1 plus 1 plus 1 plus 1. And that's going to give us 4, and we can factor that 4 out, and that's just going to leave 1 over here. And then for these last values, we again will read off 1 omega to the 6, omega to the 4, omega to the 2, and then we will have 1 omega to the 4, 1 omega to the 4, and then finally 1 omega to the 2, omega to the 4, omega to the 6. So all of those are going to cancel, and that explains all of these zeros over here. What happens if instead of having all the even values, we consider the odd values? Well, this is equivalent to an offset in the input. So here we're not starting from 0, we're starting from 1. And this offset is going to translate into a relative phase factor. That's why we have a -1 over here. Otherwise, it's the identical superposition. We have a superposition of the state 0 and the state 4. But over here, this superposition has a relative phase factor. So let's see why that happens. If we consider only the odd values, first we're going to have 1, 1, 1, and 1. Then we're going to have omega to the 7, omega to the 5, omega to the 3, and then omega. So these values are going to cancel. And the first ones, they're just going to sum to 1. And then over here, we're going to have omega to the 6, omega to the 2, omega to the 6, omega to the 2. Those will cancel. Then omega to the 5, omega to the 7, omega to the 1, and then omega to the 3. So the 3 and the 7 are going to cancel. And again, this 5 and this 1 are going to cancel. And then when we get over here, we're going to get all omega 4s. So this is omega 4, omega 4, omega 4, and omega 4. All of those values are -1. So we're going to have 4 copies of -1. So we have -4. And we can factor out the factor of 4. That's the same as 2 squared. So that is what's happening over here. And we saw these examples in the previous videos. We just didn't write them as column vectors. We wrote them as superpositions of these bit strings. So we had bit strings inside kets, and we wrote them as superpositions. So if you have all of these even terms, they're going to get mapped to the superposition of 0 and 4. And if you have all the odd terms, you're still going to get a superposition of 0 and 4, but there will be a relative phase as a consequence of this offset. So this is the first example. Now let's have a look at another example. In these examples over here, we had a separation of 2 being mapped to a separation of 4. And in these examples, we're going to have the opposite. We're going to have a separation of 4 being mapped to a separation of 2. In this initial example over here, we had a separation of 8. So if you go all the way around and come back, you have a separation of 8. And that gets mapped to a separation of 1. So we have this property of period inversion. We're flipping the period in the input state when we get to the output. And we also have this property called shift invariance. And shift invariance is the property that we were just describing over here. And it tells us that if we have an offset in the input, we're still going to get the same output except for relative phase factors. So relative phase factors in the output are consequences of a offset or an initial shift in the input. So let's see how these 4 examples work as well. In these examples, we have the normalization coefficient from the matrix, which is 2 to the -3 on 2. Then the input has a normalization coefficient of 2 to the -1/2. And we also will collect a value of 2. This 2 will come from the sum of these 2 entries. So we'll have 2 to the power 1. And when we multiply all of these terms, it's equivalent to 2 to the -1. And 2 to the -1 is the normalization coefficient of the output state. So that's what we have over here. And the output state has 4 states in a superposition. So in this first example, we can see a flipped version of what we had over here. So in this example, we took all of the even values and we turned them into 0 and 4 in a superposition. Now we're starting with 0 and 4 in a superposition, and we're turning them into a superposition of all the even values. So the inverse quantum Fourier transform and the quantum Fourier transform are actually doing the same thing to these states. That's because we're not dealing with any of the complex numbers over here. We're just dealing with purely real numbers. That is 1 over here. And the real numbers, they're not affected when we take the Hermitian adjoint, which involves taking the complex conjugate of all of the entries and also taking the transpose of the matrix. So that explains this first one. Now let's have a look at these examples. We can see that we end up getting mapped to the superposition of all of the even values. So over here we have the even values, and we also have the even values. The only difference is we're dealing with phase factors. You can see all of these phase factors appearing over here. So we don't just have ones and zeros, we have values like -1, +i, and -i. Where are these values coming from? Well, they're a consequence of the initial offset. So over here the offset is 0, so we have no phase factor. Then we have an offset of 1. We have shifted this by 1. It still has the same gap. It still has the same period of 4. But now that offset is being translated into this phase factor. That's why we have a -i, a -1, and an I over here. And what about over here where we have an offset of 2? So we have 2 units, we're offsetting, but we still have the same spacing, and that gives us these phase factors of -1 and -1 over here. And finally, if we offset by 1, 2, 3, that gets us to this state over here. So the gap is still the same. We still have a gap of 4, and it's being translated to a superposition of all the evens, but now we have this I, -1, and -i. So know that the signs on these imaginary units, I and -i, are the opposite for this case and for this case over here. And this is why it's really important to keep track of the convention, because the sign convention is going to tell you the sign of these imaginary components. And that's why I've explicitly written out this matrix representation, and I've also explicitly defined what omega is in this visual diagram and also in this Cartesian form. So let's just have a look at this example. What we have is the state at 1, and we also have the state at this value over here, which is 4 more than 1, that is 5. So we start off with 0 and 4, and then we go to 1 and 5. And then over here, we have 2 and 6, and then finally, we have 3 and 7. So let's examine this input in the context of this matrix representation. So we have this row over here, and we're just going to have 1 and 1. So the sum of 1 and 1 is going to give us 2, and we can pull out that factor of 2. That is this factor over here. And so up here, we're going to have a value of 1. The next value is going to be 0. Now, why is that the case? Well, if we look at this omega 7 appearing over here, and then if we look at this omega 3, they're both purple. That means they are additive inverses, so they will cancel. Then we have omega 6 and omega 6. That's going to give us -i. And in fact, we're going to have 2 copies of that, but we can pull out the 2 and put it into the normalization coefficient. Then we're going to have omega to the 5 and omega over here. They are inverses, so they will cancel. And then we'll have 2 copies of -1. So that explains this -1 over here. And then we have 3 and 7, which cancel. And then we have 2 and 2, and that is going to give us 2 copies of I. So that is +i. So that is why +i occurs down here. And then we're going to have omega plus omega to the 5, and those will cancel, they will give 0. Now let's examine this case where we go to 2 and we go to 6. What are we going to get? For the first value, we're going to have 1 plus 1. So that's going to give us 2, and we pull out the 2 and put it into the normalization coefficient. Then we're going to have omega to the 6 and omega to the 2. Those cancel. Over here, we're going to have omega to the 4 and omega to the 4. That's 2 copies of -1. So that explains this -1 over here. Then we're going to have 0 because we have a 2 and a 6. Those will cancel. And then we'll have 1 and 1. That's going to give us 2. And then we pull out the 2. So that explains this +1. And then we're going to have 6 and 2 again. These cancel. Then we have -1 and -1. That explains this -1. And here we have 2 and 6, and they will cancel. And finally, let's have a look at this example. So we're looking at this value over here, which is 3. That corresponds to 3. You can see 0, 1, 1 is the binary representation. And then we have a look at 7, which is 1, 1, 1. So that is this superposition. We have the superposition of 3 and 7. And the gap between these values is still 4. We just have an offset of 3. So we start off here, we have 1, and we also have 1 over here. That explains this 1. Then this 5 and this 1 are going to cancel. Here we have a 2 and a 2. That's going to give us a plus I. So now we have a plus I. It's the opposite sign to what we had over here. And then we're going to get 0 again because of 7 and 3. And then we have 4 and 4. Now that's going to give us a minus 1. And then we're going to get 0 again because of this 1 and this 5. They're going to cancel. And here we have 6 and 6. That's going to give us minus I. That's over here. And then finally, we're going to have 3 and 7, which will cancel, and then will give us 0. So you might recognize this input-output pairing. We saw this over here, these 4 examples, in the example where A equals 7. So in the video where we had A equals 7, we saw all of these mappings, and they took us from step 3 to step 4. What about these mappings over here? These appeared in the video where we had A equals 11. So where A equals 11, we mapped these inputs to these outputs. And that is how we go from the state in step 3 to the state in step 4. We apply the inverse quantum Fourier transform to the first register. And that gives us a state that we can now measure. And that is the measurement part, and that's the end of the quantum mechanical part of the quantum order finding subroutine. Then we can do post-processing, and we can take those measured values and we can put them into the continued fractions algorithm. So this is a very essential video, so that you can use this as a reference, and you can compare these representations in the column vectors to the representations where we had kets in superpositions. And you can see that this is what was used in the A equals 11 video, and these bottom 4 examples were used in the A equals 7 video. What about this example over here? Well, this showed up in both videos because step 1, the initialization procedure, and then step 2, creating superposition, this was identical for both of those examples. So this would be the state in step 1, and this over here would be the state in step 2, where we apply Hadamard gates to all 3 qubits, and that gives us a uniform superposition of all of the computational basis states. So here we have step 1 going to step 2, and then over here, what we're doing in all of these examples is we're taking a state that exists in the state in step 3, and we're mapping it to states that exist in the step 4. So that is what is happening over here. So this is 3 to 4. Over here we have 1 to 2, and then we have 3 to 4. And that leaves the question, how do we actually go from the state in step 2 to the state in step 3? Well, that's the procedure of modular exponentiation. So hopefully this video was helpful, and you can use it as a reference so you can see the specific matrix representation given all the conventions that we're using in this series.